Great. So thanks so much for having me today. I did have some strong Italian coffee, but it is 6:20 a.m. here in California, so I apologize if I sound sleepy. So yeah, as always, XQCD is right, and I keep calling him XQCD. It's XKCD. Sorry. And indeed, there's about 1 square worth of dark matter per unit Earth volume at our position in the galaxy. And no, dark matter is not squirrel. In fact, zooming out in the universe as a whole, there is very compelling evidence that 5 out of 6 grams of matter overall consist of dark matter. And if, again, you use as a unit of measurement the volume of the Earth, there's about 1 mosquito worth of dark matter on average in the universe. There's also pretty compelling evidence that the dark matter is made out of a new and as yet undiscovered elementary particle. But what is an elementary particle? Now, imagine for a minute that we're back to normal. No more social distancing, and you're out on a date, and you ask your date, and your date asks you, what do you work on? And you say, elementary particle physics. Well, she says, or he says, well, what is the meaning of elementary particle? And the best way to turn a date into a disaster, as often is the case, is to say the truth and to answer that an elementary particle is an irreducible representation, unitary representation of the Poincare group. The truth, however, has the virtue that it actually informs us. And the way in which that answer informs us is that because of Wigner's classification theorem, we know that ultimately all irreducible representations of the Poincare group are classified by 2 numbers, the mass and an integer or half integer number known as the spin. Now, if you think about the generators of the Poincare's group correspond to the generators of translations and rotations, linear and angular momentum, this actually makes a lot of sense. Now, what do we know about the mass and the spin of the dark matter? Well, first of all, quantum effects associated with the dark matter must not get in the way of what we know about dark matter halos. And so quantitatively, the de Broglie wavelength of the dark matter must be shorter than the size of the smallest collapsed halo we observe in the universe. So let's put in numbers. This requirement means that the de Broglie wavelength, so Planck's constant divided by the momentum of the particle, ought to be smaller than around 1 kiloparsec. Now, if you write the de Broglie wavelength in units of the dark matter particle mass, and you use the typical velocity dispersion of a dwarf galaxy, what you get is that the mass of the dark matter has to be greater than 10 to the negative 22 electron volts. Now, that's a very, very small number. However, we know that while we can arbitrarily stack however many bosons in the same quantum state in the same place, the same is not true for fermions. So what happens if the dark matter is in fact fermionic? Well, in that case, the phase space density is bounded from above. You can think of this as a manifestation of a Pauli blocking. And again, the upper limit comes from dwarf spheroidal galaxies where one finds the highest observed phase space density. So again, the product of the velocity and the physical density of the dark matter. So using the fact that the phase space density cannot exceed the number of internal degrees of freedom g divided by Planck's constant cubed, one can naturally extract a limit on the mass of the fermion, which is significantly stronger than the general limit based on the de Broglie wavelength. And this was figured out when I was a teeny little baby, more than 40 years ago now. It's the so-called Tremaine-Gann limit. And it boils down that fermionic dark matter in a completely model-independent way cannot be heavier, cannot be lighter than a few tenths, if you put in the right up-to-date numbers, a few hundred electron volts. Very good. So we've established that the dark matter, in a completely model independent way, has to be heavier than 10 to the negative 22 electron volts, but that if it is fermionic, it has to be more massive than about 25 electron volts or so. What happens to the other end of the dark matter as a new constituent? What is the upper limit to the dark matter particle mass? Well, ultramassive dark matter cannot be spoken of in terms of the language of elementary particles. If your dark matter candidate is much heavier than the Planck scale, then one ought to talk about composite objects or objects such as primordial black holes, which also quite interestingly can be spoken of in terms of exactly the same quantities that Wigner's classification theorem talks about, so the spin and the mass. I'll spend the last part of my talk talking about primordial black holes as dark matter. But coming back to the question, how heavy can the dark matter be? What is really key phenomenologically is the fact that very heavy dark matter, if it is point-like, would act exactly like a bullet and destroy some of the beautiful structures that we observe being very resilient in the universe, such as globular clusters or disk galaxies with very, very stable disky structures that survive, as far as we can tell, indefinitely in the universe. And so, again, one can put in numbers and this is not a horribly complicated calculation, and you can convince yourself that the upper limit is about 1,000 solar masses or so in quite model-independent way. And if you express this in the same units that we were using before, this means 10 to the 70 electron volts. So the landscape of dark matter particle masses, sort of following up on the last question that Matt received, does the dark matter necessarily need to lie at the electroweak scale? Well, the landscape is incredibly wider than that. And it really goes from 10 to the negative 22 electron volts all the way up to 10 to the 70, being bracketed by macroscopic quantum effects on the one hand and macroscopic tidal effects on the other hand. So what else do we know about the dark matter? Well, actually, one thing that goes to answer the ambitious title of my talk is that the standard model actually does contain some of the dark matter in the form of neutrinos. So how much of it is that? Well, neutrinos are hot relics. They thermally decouple from the universe's thermal bath at about 1 mega electron volt temperature. And the calculation of the thermal abundance of hot relics, relics that decouple while relativistic at a temperature much greater than their mass, is very simple. I don't have time to go through the calculation, but the key result is that in units of the critical density, the contribution of a hot relic as part of the universe's energy density scales linearly with the mass of the relic. And in the case of neutrinos, so for the number of degrees of freedom that the universe had at the time of neutrino decoupling, this gives a numerical coefficient that is 91.5 electron volts in these units. Now, we know that at least 2 neutrinos are massive because we observe neutrino oscillations. Solar and atmospheric neutrinos tell us that we have at least 2 different mass scales. And so even assuming that the third neutrino species that we do need for oscillations to take place is massless, at a minimum, we have to have that the dark matter contributes slightly over 0.5% of the dark matter in the universe. So that's quite interesting. What about the upper limit? How much of the dark matter can be in neutrinos? And of course, this is a huge field that, again, I don't have time to go through. But neutrinos, being hot relics, sort of tend to form structures in the wrong way in the early universe, tend to suppress very strongly small-scale structures, tend to dampen small-scale oscillations in a matter density power spectrum. And so CMB constraints, for example, limit the mass of the neutrinos, the total mass, so the sum over all neutrino species, to be below 0.3 to 1.3 eV. And if one adds a more comprehensive set of large-scale structure data, this limit actually goes down to about 0.17 electron volts at a 95% confidence level. So putting a standard model component of neutrinos as dark matter at most 1.6% of the dark matter budget. So yes, we do know what around 1% of the dark matter is, but what about the remaining 99%? Well, we know it's squirrel, we know it's non-mosquitoes, and we know that there's this huge landscape. So for many years, we've fallen in love with one particular range across the vast landscape, the weak scale. And we've devoted a lot of time and a lot of creativity and a lot of taxpayer dollars and euros to build experiments looking for dark matter in this particular corner of the parameter space around the electroweak scale. Now, if you put things in perspective in this very large landscape of dark matter candidates, that scale and the scope of those experiments is fairly limited. Now, to be absolutely clear, the assumption that goes into falling in love with the electroweak scale essentially boiled down to the fact that if you consider a thermal relic, and if you assume that the interactions of that thermal relic with the standard model are weak, so they are mediated by SU2 left of the standard model, then indeed you fall within this particular range. Now, the same sort of WIMP miracle that tells you that you get the right relic density pretty much for any mass or logarithmic clean mass, as long as your cross-section is in units of inverse GeV squared of the order of 10 to the negative 8, allows you to, as my colleagues at UC Irvine call it, consider a WIMP-less miracle that includes a slightly bigger range of masses. But of course, there's a price to this, and the price is you have to invent new interactions between the dark matter and the standard model besides SU2 left. So today I want to take you in a journey across this vast landscape of dark matter, and necessarily my journey has to be quite hasty. I want to start by mentioning what people have come to refer to as fuzzy dark matter. These are dark matter candidates that are indeed such that their quantum effects are macroscopic. And so their masses, they have to be bosonic, and their masses are on the order of 10 to the negative 22 electron volts or thereabouts. So one general feature of this class of models is that they've got a soliton-like core, and the soliton core has a size that is inversely proportional to the velocity dispersion of the halo that these particles live in. Now, another interesting feature of these models is that you can test them observationally. And in fact, it's quite interesting that new stellar surveys, including, for example, Gaia or even Euclid, will offer a lot of opportunities to constrain the velocity dispersion and a density profile of dark matter halos in a way that would test whether or not these candidates are in fact viable. I have to say that some people sell these candidates as possible solutions to known small-scale structure issues in the cold dark matter paradigm. Well, that's a bit optimistic. In fact, it has been shown that using 21 centimeter line data, there are already very strong constraints, and one anticipates to have even stronger constraints in the future that will essentially negate the possibility that the quantum aspects of dark matter as an elementary particle could be used to solve the small-scale issues of the CDM paradigm. In the next talk, Andreas will explain everything about light bosonic dark matter, sort of a generalization of axioms. There are many exciting new ideas, and there's a lot of creativity that investigators are putting in, trying to sort of generalize sort of older ideas on how to detect axioms, essentially employing galactic halo radios to tune on the frequency corresponding to the mass of these objects and trying to go after them. So I will not really spend any time on this topic right now. Let me tell you a little bit about stellar neutrinos. Now, stellar neutrinos, what we mean by that is neutrinos that are not charged under SU2 left. We might need them for a variety of reasons, including, as I mentioned, the fact that neutrinos do exhibit mixing and certainly have at least two of them masses, and we don't really know how to give them a mass in the standard model, but the simplest way is probably to add a sterile component to the particle content of standard model. Of interest to dark matter phenomenology is that the stellar neutrinos generally mix with active neutrinos and they decay. They, of course, prefer not to decay through this channel. They prefer to decay into 3 active neutrinos, but every once in a while, they also decay into 2-body final states that include a photon. And since the dark matter is today essentially at rest, the photon energy that you get in the 2-body final state with essentially massless particles corresponds to half the rest mass of the dark matter. And so if you see, just to put out there a number, a line at 3.5 keV, that could originate from the decay of a 7 keV or so stellar neutrinos. Now, of course, we've all heard about this 3.5 keV line that was detected by Ezra Bulbul and others in the stacked images of in X-ray of clusters of galaxies. It has been confirmed by other groups. Myself and Tessa Giacomo at UCSC discovered this line from the galactic center. And so there was a lot of activity related to whether or not the line could originate from the decay of stellar neutrinos. The answer is right now that for sure the line cannot come from decaying dark matter. It's very conclusive evidence at this point in time. And the 2 key pieces of evidence have come from 2 observations. One is a 1 megasecond long observation of one of the most boring possible places in the universe, which is a dwarf galaxy, Draco, satellite of the Milky Way. Absolutely no sign of the 3.5 keV line in this dark matter dominated system that is nearby enough that if the line originated from dark matter, there would have been a clear signal. It's not there. And this was pointed out by Tessa Giacomo and myself a few years back. There's also a really important result that just appeared on Science by Dessert and others that used XMM blank fields to conclusively show that at least by 1 order of magnitude, the flux of dark matter you receive through dark matter decaying inside the galactic halo in these blank field directions observed in the sky by XMM, there's no signal there as well. So for sure, a 3.5 keV line cannot originate from stellar neutrinos. There was a lot of enthusiasm. We still don't know what the line is. There is an experimental program that will tell us something about the nature of this line, but at the moment, that's where the status is. So let me tell you a little bit about WIMPs, about weak scale dark matter candidates. As we heard in Matt's excellent talk, these are common in beyond the standard model weak scale paradigms. There's a very advanced direct detection program that so far has included no positive detections, and one can say confidently, despite repeated claims by my fellow countrymen at the DAMA experiment. There are a few controversial indirect dark matter signals, and that's what I'm going to comment upon here briefly. So Matt already commented on the galactic center axis. Now, what Matt did not emphasize is that there are key issues with the actual determination of the galactic center axis, and that's primarily what I've been working on. And these issues have to do with where cosmic rays that produce the bulk of the galactic emission of gamma rays, including at the galactic centers, where these cosmic ray sources are. So now, why do cosmic rays source something that manifests in gamma rays? Well, the reason is that primary proton cosmic rays impinge on interstellar material and essentially on nuclei in the ISM, and the inelastic collisions produce a lot of pions, including neutral pions, and then decay into 2 photons. The diffusion models that people employ are also very simplistic, more on that later. And as Matt did emphasize, there are unresolved gamma ray sources, while the contribution of these sources to the galactic center axis is and continues to be a hot topic of debate. So this is what the axis looks like. Let me just draw your attention to a work that I carried out with my then graduate students, Eric Carlson and Tim Linden, who's now a professor at Stockholm University. So what we did was to say, well, maybe it's not a good idea to place cosmic ray sources in a donut, which is what pretty much every galactic diffuse gamma ray background model does. Rather, we should put the galactic cosmic ray sources where cosmic ray sources should be, which corresponds to where stars die, which also corresponds to where stars are born, which in turn corresponds or is traced by where molecular hydrogen is. And so we stuck a bunch of cosmic ray sources in these regions. There's a face view of the face-on view of the galaxy. And if you do that, essentially the nature of the axis changes drastically, and the axis itself can be explained away. And I point you to Tim Linden and his follow-up work for more of this. There are out there several other gamma ray axes that myself and others are investigating. There's a very interesting one from M31, the Andromeda Galaxy, 0.7 megaparsecs away. There's a very interesting axis outside in the outer halo of M31, which probably cannot be explained with background cosmic ray emission. There's an axis in Omega Cen, which, while thought to be a globular cluster, might very well be an ancient dwarf spheroidal galaxy. And these are all very interesting things that we should look in. Another controversial indirect signal that I spent quite a bit of time thinking about is the positron axis. This is very convincingly an axis with respect to sort of the standard anticipated background from cosmic rays. So there's no way that within a normal cosmic ray model you can explain a secondary product such as positrons that would fit the axis of positrons observed in a cosmic radiation of about 100 GeV. I don't have time to go through this. I'm only going to mention that that there has been a key recent result from a very high energy gamma ray telescope called HAWK, a water Cherenkov detector that observed macroscopic structures around nearby pulsars, Geminga and Monogem, that show that very high energy electrons diffuse very, very slowly around these pulsars. Now, why are pulsars interesting? Well, they are interesting because it's shown here, precisely those two pulsars give a beautiful fit to the positron axis on top of the background. And this was pointed out by myself and others many, many years ago. So the HAWK result by itself would negate the possibility that Monogem and Geminga produce the positrons that we observe at Earth, because the shape and the scale of these TeV halos around the pulsars is such that the diffusion of positrons in a galaxy would be too inefficient for these particles to reach us before losing most of their energy along the way. So, well, are pulsars now ruled out as an explanation to the positron axis? And do we have to go back to the drawing board and build dark matter models that many hundreds of investigators have done, including myself? Probably not. So what I've done with my junior collaborators, Javier Reynoso and Maya Silverman, was to ask the question, well, what if diffusion is indeed, as measured by HAWK, inefficient within pulsar wind nebulae, but it transitions to a reasonably large value right outside the nebulae as we need to fit other cosmic ray data? Well, if that's the case, and this actually is very plausible from the standpoint of the theory of cosmic rays, then pulsars are back in a game and they can explain the axis of positrons without the need of dark matter. So that minimal explanation is still alive, but the model of diffusion of cosmic rays we have has to be modified And at least it has to include the fact that there are these pockets where the diffusion coefficient is at least a factor of 100 less large than in the galaxy as a whole. There's also an antiproton excess that is claimed at a couple of different energy ranges. I have serious doubts about that. I think there's enough leeway in cosmic ray diffusion to take that into account. And AMSO2 on board the International Space Station has also observed roughly one event a year of very heavy anti-nuclei event, very heavy from, for as long as cosmic ray experiments are concerned. And so these anti-helium-3 and anti-helium-4 events are completely mysterious. They cannot originate from standard processes. There's been speculation that they could originate from antimatter domains that have to be very close by. It has been speculated that they come from dark matter annihilation. So stay tuned. It's probably an artifact, an instrumental artifact where these anti-heavy nuclei are actually normal matter nuclei that take a weird trajectory inside the tracker of AMSO2 and are mis-tagged as anti-nuclei events.
5 minutes.
Very good. So in these 5 minutes, I'm going to flash through one class of candidates that has been very dear to my heart as of late. And these are candidates that live to the right, where Planck's smiley face is in this landscape of dark matter candidates. So one thing that caught our interest is that if you have a candidate right about the Planck scale, well, generally you would think that's very hard to detect. But if you're lucky enough that that candidate is charged, then some hope is there. And if you think about black holes, and if you think about primordial black holes that evaporate very quickly if they're light enough, then you might get stuck with a relic electric charge. So, in principle, black holes that evaporate into any particle that has a mass of the order of light or lighter than the Hawking temperature of the black hole. So generally, you will evaporate into charged particles as well. And it's been known for many years that black holes could get a relic electric charge in that way. So with my student Ben Lemon, what we've done is we've convinced ourselves that that's very plausible. It's very plausible that a fraction here indicated by FCPR of primordial black holes in a mass range close to the Planck scale might be charged. And if that's the case, we can use dark matter detectors to search for these relic objects. And it turns out that neutrino experiments are actually great for that purpose. And old experiments like macro that were built initially to detect gut scale monopoles are also great. But the most interesting thing that we find is that instead of building very big experiments, you can deal with the fact that supermassive dark matter particles have very low fluxes by extending the time scale of your detectors. And you can do that with Pauli detectors. And so even a centimeter squared Pauli detector that's been around for a giga year could have an imprint of the passage of a very slow charged particle if it's been around for a giga year or so. And so ancient mica seems to be the most promising material that could inform us on whether or not these relics really are around. And we could probe fractions of the dark matter that are significantly smaller than, for example, the fraction of the dark matter that we know is instead of in active neutrinos. So even if PBH are not the dark matter, they can produce dark matter via Hawking evaporation. I have no time to go into the details of this mechanism that, thanks to my Greek-American student, John Tamanas, we dubbed cleverly melanopogenesis. Here, the idea that I've worked on with my students, Logan Morrison and Yan Yu, is that primordial black holes can evaporate in ordinary and dark matter, and you can produce the right amount of dark matter as a result of black hole evaporation once you know essentially only one thing, which is the number of degrees of freedom of the dark sector that eventually decays into your dark matter particle. And so knowing that, you can calculate in the plane of the mass of the PBH versus the relative abundance of PBH at PBH birth. You can calculate where on this parameter space you want to be. You can also produce matter, antimatter asymmetry in this mechanism through, for example, evaporation into neutrinos and subsequent stereo-neutrinos and subsequent leptogenesis. So I don't have time to go through this, but what we do find is that you can have the right amount of dark matter in the form of stuff that you've evaporated into, and or in the form of relics that could get to stability and end evaporation at or around the Planck scale. And so there's a scenario where you can do baryogenesis as well as having a mixed dark matter scenario with relic at the Planck scale right here, plus dark matter that you have evaporated into. Now, one last thing I wanted to bring to your attention is that a lot of the things that we've been taught about primordial black holes, now that there's a renewed enthusiasm about this class of candidates, has been revised. And in particular, this plot that shows the fraction of primordial black hole that can be the dark matter as a function of the primordial black hole mass in units, notice of the solar mass. Well, this plot is wrong, and it's especially wrong in these two places. So let me in particular comment on stellar mass black holes, which, to quote an old wise man that played a very big role in the discovery of gravitational waves, the black holes that we are seeing with LIGO were a little heavier than we expected. So there are a bunch of unknown things about stellar mass black holes that have prompted people to think of them as possible dark matter candidates that I think should be clarified. And so we're working on this. In particular, one question is, how does accretion around stellar mass black holes work, especially of the combination? This seems to be one of the strongest constraints, together with the rate at which these objects have to merge. The spins of these objects looks a lot like the spin you would predict from PBH that formed in a radiation-dominated background. It's very low, and that's unlike what you expect from stellar mass black holes of astrophysical origin. So that's also interesting. It might be that there's some new physics scenario that explains the spins being so low because, for example, of superradiance, so the ability of black holes to shed angular momentum in the form of ultralight particles of the type that, for instance, Andreas will talk about after my talk. What I really am hopeful about is that we will see a sub-Chandrasekhar black hole merger with LIGO. That is a distinct possibility. And in fact, with my student Ben Lehman, we are working on calculating what is the expected rate if indeed we have some population of primordial black holes that is massive enough to be visible at black hole mergers at LIGO, but below the Chandrasekhar mass. And so these objects, if indeed seen with LIGO, would immediately be recognized as being of non-astrophysical origin, so presumably of primordial origin. So that's extraordinarily exciting, so stay tuned there. Now, what I want to comment on, and this truly is the last thing I'm going to tell you guys today, is how this part of the plot is wrong. And this is recent work with Nolan Smith, who gave a wonderful talk yesterday at this conference. So the idea is to use Subaru HSC data that looked at the Andromeda galaxy, and specifically about 1 million massive stars in the Andromeda galaxy, searching for microlensing. Now I'm going to explain to you how microlensing works, but I assume you know what this is. The key point is that the limits that the collaboration that first studied this put out did not take into account finite size source effects. And it so turns out that they used, even after they corrected for this effect, the size of the stars being all equal to 1 stellar radius, but that is completely wrong. The sun would not be visible by the Subaru HSC camera at all. And so microlensing events could not originate from suns size stars. The stars that do contribute, and this is the key of the work we've done, are much, much bigger. And if stars are large, then finite size source effects matter. Let me give you a very, very quick explanation as to why that is. So this is what microlensing ultimately is. You lens light that would not get to your telescope, but if the star is large, you get a lot of light from a much wider region than where the light that would be lensed would get to you. And so you essentially nullify the microlensing effect if the star is large enough. And what that means is that you move the constraints from what was calculated by the HSC collaboration folks down to much smaller mass scales. And that is the gist of our result, which has now freed up a huge swath of parameter space where primordial black holes can be the dark matter. Notice that other constraints here are also affected by finite size source effects. For example, femtolensing constraints at smaller mass scales. So the question is, how do we go after this broad range of masses that are unconstrained by microlensing or femtolensing? And one possibility that we are looking into is to capture these objects and to study the gravitational perturbations that these objects would induce on planets or on pulsar binaries or on similar objects. So to conclude, we know what about 1% of the dark matter is. That's standard model neutrinos. We also know that dark matter is neither squirrels nor mosquitoes. I've told you a little bit about fuzzy dark matter, light bosons, stellar neutrinos, WIMPs, Planck scale objects, asteroid mass black holes that again can be 100% of the dark matter once finite size source effects are taken into account, and stellar mass black holes. I'm going to stop here. I thank you very much for your attention, and I will take questions.